Is that okay? Now for volume charge distribution, I have to write my dq rho d2 into v. Wait a second. What is this potential? What is that potential at the point of charge? At the position of charge. What is this potential? At the position of that small elementary charge. Don't forget that one. Okay. Where this runs? This runs in the region of the charge. Outside the region, potential exists. Remember. But you have to run that summation runs only. So in the region of the charges. Am I right? Same thing is extended. This volume integral. If you talk about volume integral, that volume integral runs in the region of the charge. Is that okay? Now that's equal to, so half of integral of rho v d2. Can I write like this? Volume integral. That is the total electrostatic energy stored in the system. Now we have one small derivation here quickly. So rho, I can write it as epsilon naught into del dot E according to Gauss law. Check it out. So epsilon naught by 2, I'll take that epsilon naught outside, del dot E into scalar V d2. Am I right? Volume integral. Epsilon naught into del dot E, that is rho. Okay. Now from last chapter, I think I have taken one integration by parts kind of thing in case of divergence like that. So if I apply that one, what would happen here? That's equal to epsilon naught by 2 outside, okay, minus integral E dot del V d2, E dot del V d2 plus closed surface integral of V into electric field dot dA. Yeah, pick out. Again, one vector calculus theorem involved from here to here, okay. Again from last chapter, I think I mentioned this one, okay. While studying, I mentioned this one. We need this one. Is that okay? Now, what is this volume that we have taken? That is the volume which runs in the region of the charges. Am I right? Because we have started with this integral. That is the volume integral that runs in the region of the charges. Is that okay? Now, I do one thing. Yeah, what is this surface? This surface is the surface, boundary of this volume. Is that okay? That's closed surface, which is the boundary of this volume, or surface which encloses this volume. Okay. Now, what I do here is I am going to take very big volume. Very big volume. I am going to extend that one. So, so among those only again, okay, so remember. So, let me again start with this one. If I run this integral, so from entire region, so out to infinity, then so there is no loss. Am I right? Why? Because charge density, whenever charge density is non-zero, it will be non-zero. Outside that one, it is zero. Let me go back to this one. This is the volume integral in the region of the charge. Okay, I have some region of the charge. I have volume charge density. Now, what I have done this volume integral. Now, what I do here is I am going to do that volume integral in the entire space, including infinity. Okay, entire, so out to infinity. So then what will happen? It will take care. This rho will take care actually. So here in this one, this del dot E will take care. Del dot E is 0 outside the region of the charge. It will take care. I can just make that volume integral infinitely large throughout entire space. When I do that one, look at here, keep on looking at that one. What is this surface? That surface will be at infinity now. Isn't it? So, when that surface is at infinity, again, what is surface integral? In that surface integral, you have to take field on the surface, remember. Now, surface is at infinity. This is the finite charge distribution. The surface is at infinity, so that's why your electric field and potentials are very small at infinity or 0 at infinity. So this part will be 0. Are you getting the argument? Okay, extending this volume integral throughout the region of, so I mean entire space, okay, so that this surface integral will become surface at infinity. Okay, so now what would happen here is, so once that part is 0, your work done is equal to epsilon naught by 2 integral E. Let me take this minus inside. What is minus del V? E. E dot E d2 integral over all space. This will be surface at infinity only when you integrate over all space, remember. Integration over all region of the space. So that again your boundary is at infinity. Boundary of the boundary of the region, whatever you are talking about, that is at infinity. So that is epsilon naught by 2 integral E square d2 all space. Now carefully see these two formulas. A lot of question will arise actually. Integral over all space, don't forget. This was integral over region of the charge. This was integral over all space, wherever the field exists, isn't it? Now the question is whether your energy is stored in the form of charge or in the form of field. When you see this one, when you see when you see this one, look at here. It seems like energy is a kind, I mean, it's stored in the form of charges, am I right? You have charges in space. But here, it looks like energy is stored in the form of field, am I right? Just see his comments on this one. Again, I'll not go a little deeper here because we will get many inconsistencies here. So now this is always positive. This is always positive. Look at here. E square of the vector field and d2 volume integral. That's always positive, but this can be either positive or negative. Isn't it? For positive, so suppose rho is negative, then I mean, so there may be some situation. Obviously, potential energy can be negative, am I right? Suppose if you have negative charge, you have positive test charge. If you are moving from infinity to that point, your potential energy is negative, isn't it? So energy stored in the field is negative now. I mean, energy stored in the system will be negative now, okay? This will allow positive as well as negative total energy, but this will not. Lot of inconsistency in that one. He just discussed this one here. Comments on electrostatic energy and inconsistency, okay? So let me just avoid that one. Let us solve some problem on that one, okay? So let me just explain later. Yeah, any questions? Just read out his comment on this inconsistency, okay? So now let me do example number 2.9. Now while again this is the total electrostatic energy, both of them in case of continuous charge distribution usually. For finite charge distribution, you don't have to go for this formula, you can just do it like this, isn't it? So that's earlier problem. This is for continuous charge distribution, total electrostatic energy. Find the energy of uniformly charged spherical shell of total charge Q and radius r. Spherical shell of total charge Q on the surface and radius r. Now which one you are going to use? If you want to use this one, you can use this one. But you need to do again. So you have to go for this one. We have to write dq is equal to sigma dA. You can do that one, okay, but that integral may be little lengthy, okay, or you can do that one. I think he might have done that one. Yeah, let me do in both ways. Okay, let me do in both ways. So W is equal to half of sigma dA V. What is V? V is the potential in the place of charges. Then V is the potential on the surface. Remember, you have to define that one. What is V on the surface? 1 by 4 pi epsilon naught Q by capital R. It is continuous, isn't it? Potential is continuous, isn't it? Inside potential is same. Outside potential is 1 by 4 pi epsilon naught Q by small r. Isn't it? Spherical shell. Is that okay? So now look at here, 1 by 2. So what is this dA actually? This is actually dAr actually. Don't write in vector form. Isn't it? That is the surface here. Am I right? You have to take surface like this. And you have to take potential in the position of the surface. Is that okay? Sigma dAr. So that's sigma also outside. Potential also outside. Am I right? Potential is also constant throughout this region of the charges. So that is integral of dAr. What is that one? That is total surface area. 4 pi r square. What is this one? Total? Yeah, sigma into 4 pi r square. What is that one? Total charge. So Q into V on the surface. But write on. Potential on the surface. Yeah? Oh, okay. I forgot divide by 2, divide by 2, divide by 2. Ultimately, again, look at here. I avoided that coordinate geometry again. Isn't it? I just have seen that there should be total surface area. I just written that one. Is that okay? Otherwise, you have to do that integrals, isn't it? That's unnecessary. So, what is this one? Ultimately, 1 by 8 pi epsilon naught Q square by R. Can I write like that? Check it out. Why Q here? One more Q inside here. 1 by 2 here, 1 by 4 pi epsilon naught. So, in this, while applying this one, we have to take potential in the region of the charge and we have to integrate that. That is one possibility. Other possibilities, you can go for this one. What is the electric field inside? That is 0. You don't have to integrate inside. But in this integral, you have to integrate entire region of the space. Is that okay? But you don't have to take in the electric field inside. Look at here. Electric field outside or electric field is equal to, look at here, that's 0. When R is less than R, that's equal to 1 by 4 pi epsilon naught Q by R square R cap when R is greater than R. Am I right? Now, what is E square of this one? Isn't it? The square of this one. Integrate that one from R to infinity. Not 0 to infinity. 0 to R, it is 0. Is that okay? Volume integrate that one. Epsilon naught by 2. 1 by 4 pi epsilon naught the whole square. I think Q square. 1 by R raised to 4. What is d tau? D tau will be there. E square d tau. R square dr sin theta d theta d phi R square R cube by 3. Yeah, what it will be? Anything is missing? Correct? You have to integrate R from R to infinity, theta and phi as it is. Outside the region, because inside electric field is 0. Just check it out. What is that integral? You will get the same. Okay, 1 by R square R to infinity dr into 4 phi. Am I right? Minus 1 by R, infinity to R, I think positive. Am I right? Lower limit, upper limit is 0. 4 phi, one of the 4 phi got cancelled. One of the epsilon naught got cancelled. 1 by 2 Q square by 4 phi epsilon naught 1 by R. You will get that one. You will get the same answer. Do that integral. 4 phi due to sin theta d theta d phi. Integration of sin theta d theta d phi. There is no other functionality. Theta and phi. Okay. Do that integral. I hope you know how to do this one. Go to that coordinate geometry and do that one. And you should know where you have to integrate. You have to integrate outside the region of this shell. Why? Inside electric field is 0. Okay. Now look at the difference here. This here we integrated in the region of charge. There we integrated entire region of the space. So that is the total electrostatic energy stored. Okay. Now let me extend this question. This is the next question that is asked in CSIR JEST exams. 2.34, 34th problem. Okay. I have solid sphere. I mean, now my charges are uniformly distributed. Okay. So what is the total electrostatic energy? What is the total electrostatic energy? How do you start? Now, if you want to use this one, you should know what is the potential inside, because inside you have a charge. Is that okay? If you want to use this one, you should know electric field in all regions. Inside also you have electric field, isn't it? What is the best idea? I think electric field is the best idea, because you don't remember, I think, potential inside this one, isn't it? Potential inside that one was a two line integral. That was a little difficult, isn't it? Now you have to decide which method you have to follow, isn't it? It is unnecessary. Why? You don't know potential. You know potential outside, you don't know potential inside, isn't it? You don't need potential outside. Outside you don't have charge. This volume integral runs in the region of the charge, and you have volume charge density. That's why I better to use that one. As I remember, outside electric field is 1 by 4/5 epsilon naught Q by R square R cap. Q is the total charge. So what is electric field inside? 1 by 4/5 epsilon naught Q by R cube R cap. Am I right? Now do that integral. Now you have to split the integral, because 0 to capital R one type of functionality, R to infinity other type of functionality, isn't it? Electric field. So that's why. So W is equal to epsilon naught by 2 integral over all space. Let me write 0 to R, R to infinity. Am I right? Can I write like this? E square d2, E square d2, E out, E in, E in, E out. Can you quickly do this one? Epsilon naught by 2. Let me write some step directly. Try it yourself. Epsilon naught to the whole square, 4 phi due to sine theta d theta d phi. Okay. Q square, it's also common. Inside 0 to R, R square dr from d2, 4 phi from sine theta d theta d phi. I have already taken. 1 by R cube, R by R cube, plus R to infinity 1 by R square dr. Wait, something is missing. R raised to 4, 6 square, isn't it? Squared, isn't it? E square. Otherwise it would be infinite, isn't it? Now this is 1 by 8 phi epsilon naught as earlier. Q square, 4 phi, one more epsilon naught here. What is this one? Any idea? 1 by R power 6. R power 5 by 5. R power 5 by 5 plus 1 by R. Ultimately, it is 1 by R common, 1 by 5 plus 1. Am I right? 1 by 8 phi epsilon naught Q square by R, 1 by 5 plus 1. Check it out. 6 by 5. Okay. He asked the ratio. He asked the ratio for shell and for solid sphere. You have charges only on the surface. You have surface charge density. you have charges, same radius, okay? Same radius. Same radius, but total charge is also same. Same radius, total charge is also same. Is that okay? But here you got total electrostatic energy 1 by 8 pi epsilon naught q by r, am I right? Here you got 6 by 5 times 1 by 8 pi epsilon naught q by r. Why higher here? That he asked that question, okay? Why higher here? Total amount of charge is same. He asked the ratio, okay? Ratio of these two. Any reason? Okay. So, here concentrated on the surface. So from which discussion we have started this one? We started moving the charges from infinity to point, infinity to in our region, right? Accumulating the charges. Yeah, we need to move charges little more distance against the repulsion to have this configuration than this one, isn't it? Here you have to move to the surface. Now you have to move inside again, isn't it? So that's why this will have little higher, 6 by 5. Okay, little higher than this one. Okay, you can use that one to eliminate options sometimes. This will always have higher electrostatic energy than this one. Shell. Yeah, any question? Q by Q square, both cases Q square. Otherwise it's not energy. Am I right? It's not energy. So there are very less questions on dimensional analysis, okay? But there are questions still. Sometimes if they don't take care while designing the option, definitely you can do dimensional analysis. Is that okay? There are many 5 marks questions that you can do like that, but you should not depend on it. Okay? Yeah. Q square, obviously. Energy. Yeah. Now do problem number 36 and 37. 2.36, 2.37. (34), 36 and 37. Okay, we shall discuss about conductors. Again, I have to discuss particle physics. That's by tomorrow only. Okay. Let me finish out that conductors in the evening. Okay, discussion on conductors and capacitors. Only those two concepts remain, and you need to solve much outside problem from this chapter. Again, we can go for next chapter. Okay. You better to prepare your mind to not to take a holiday during Diwali. Is that okay? Sacrifice Diwali holiday because you have taken holidays for Dasara. Isn't it? Again, we are a little lagging here. Okay. This is electrostatic. I have potential chapter. I have electric fields in matter. I have magnetostatic, magnetic fields in matter, electrodynamics, electromagnetic waves, potentials, radiation, field transformation, relativity. Is that okay? Within this month. Okay? Mission impossible. Yeah, we have to do that. Okay. Yeah, once you are good in those mathematics, I can finish out quickly. Okay. Initially, it may take some time. Later, I'm going to tell this is the surface, this is the volume. Just do that one. Okay.